Hi everybody. Today I want to talk to you about one thing that's probably the most important thing in the real life, and it's around friction. Friction with deep learning models. And if there's something that's really underappreciated is the fact that deep learning models can add value, but if there's friction, you just collapse the entire thing. So if there's one thing you should be obsessed about is friction. And in this talk, we'll go through a couple of examples of why we're obsessed with that. It's a bit of a lightweight talk compared to Stuart, so it's not as intense. So and we'll also share some ideas or stuff we came across over the last few years that helped us to reduce this friction. And essentially, why this friction thing? You know, how do you reduce it or remove it? And it's all about this seamless integration between tech and people. Now often you've got a nice toy, you've got a nice new tool or model, and you use it, but if you don't use it in a seamless way, you're just introducing more friction. And this friction becomes a problem if you scale. If in the real life, if you scale, if you move it into production, any sort of friction that at the time doesn't feel like anything just becomes like crippling. And why is friction important in the real world? Because the problems are hard. It's if you look at data sets, nothing is like the standard images or CFRNet or you've got these nice sort of libraries that you just pull data down and works. The reality is data is all over the show. In sort of the finance game is we essentially have to buy data. So data comes from people, systems, legacy tools. So it's complex. And the other thing, markets change. Things change, models change over time. So what you do today compared to yesterday it's not always, you constantly got to evolve, which adds another dimension or hyperparameter to the whole exercise. Then the basic things are non-linear. So unlike an image in the academic world, you might have an image and you've got nice pixels and depth. And in some of these real world examples, there's none of that. So you've got to come up with features. You've got to look for sources. You've got to engineer stuff. So it's a lot of the things haven't been solved. And obviously the search space is quite large. You think you build a model and then after a while you think, what about this? What about that? And suddenly you just scale up. All the potential options just blows up. And then the last thing, if you build a model and and it's not good enough and you miss something, you get sort of a false negative. What happens then? You move on. But to move back and sort of revisit that hypothesis becomes quite hard. And in all of these things, if friction is there, it just becomes like a whole next level. So what have we done to sort of, how do we structure this problem of friction? You've got a nice circle here, and you start off with your machine learning models. It's nothing new. We're all here for that. It's pretty cool. Building models are cool. Building models are becoming easier. There's a lot of tailwind, a lot of open source out there. But they need features. They need data. So you've got this pipeline. And at the moment, you look at this curve and you say, cool, it's a nice, clean chart. But there's no humans really involved in the domain side of things. Now, just in our example, there's a bench of analysts, traditional fund managers. And what they do, they look at the markets all day. And looking for ideas. They don't care about machine learning. They don't care about sort of our nice graph here. But we've got to integrate them. So one way of integrating them is bringing these black box models and converting them into portfolios. Now, suddenly these portfolio managers then they look at a portfolio, they understand portfolio, they look at all the factor exposure and all the bells and whistles that are super populated across the finance. Where you do your risk analytics and et cetera, et cetera. There's just a ton of tools out there. So suddenly you have this human in the loop. Okay, so how do you incorporate that? Can add a lot of friction to the setup. So you do some trading and you've got a nice clean diagram that everybody's sort of happy with. So in the reality, it looks quite different. It's way more complex, and it probably looks like something like this. So what this is, you can see every dot, if you look at any of those dots, every dot is a service. Okay, a service might be a particular quest, a particular data extract, a particular data pipeline, running a model, doing a prediction. So when you look at the dot, it's very defined and easy to understand. But when you start blending these things together, the complexity becomes. And with complexity, you get just more and more friction. So you gotta have a framework in which you can highlight these frictions quite easily. Now, so what we did, we built what we called, this is now meet Alice time. Who's Alice? This is Alice. And it's essentially an event-based operating system that just allows one to frictionlessly develop and try and test new ideas. And so now you've got, let's call Alice is the tech side, that's the sort of non-human side of all of this, is how do you integrate Alice into the team? And there's a couple of things. So let's look at the team. The team is let's say in this case, it's a distributed group of developers and experts in what they do. Now, these guys have been involved on sort of contract basis, or some of them are still very active in part of the core team. On the left, we've essentially got a Boston-based and Johannesburg are the two main nodes. But these people are all distributed across. Now, if you've got your communication channels, it's problems that have been solved through decent technologies. So let's assume that the communication between all of these points are spot on. And let's bring them all together in one room. So you've got this nice grid with all people sitting there. There's myself and Zander, this sort of Zander next to me here. And the communication is frictionless. We're on the same page, we're in the same office, we talk, and we exchange events. Let's call me asking for Zander for something. It's me asking, sending an event to Zander, and he acts on that event. So within this team, these are just sort of names of some people, but like there's Mo. Mo, for example, is one of our analysts. Now we've got access to, within the group, to CFAs and really people in the domain that doesn't care about Alice. It doesn't care about the tech stack. We've got who else? Nadie. Nadie is a visual expert. She's a monster with D3 visuals, and she helped, for example, with solving a few visual problems we had, which we weren't able to do with a standard set of tools. Now, so you've got all these people, and they talk well, and the system is online, and you know who's doing what. And then you have Alice, which is really at the top. You can see that at the top left. So one of the ways to reduce friction is to bring Alice into the team, as if Alice is another person. So Alice is another dot in this diagram, and Alice communicates. Alice sends events. We look at Alice. So let's pretend Alice is actually a person in the team. Something different. Alice, because Alice is obviously the tech side, it's all over. So Alice needs to integrate quite well with everybody. So Alice is everywhere, and some of these people don't even know Alice is not a machine. So it's just playing with that idea with a seamless integration, so that you don't get a nice new tool, a nice new model, and you try to force it down in the team, and it doesn't. It just adds friction. It's like a kid with a new toy or a new risk model that you just want to show everybody, and it's actually interfering in the normal process. So how we solve this Alice human in the loop setup is three things. The first is the communication. So this is just a quick screen recording of essentially that visual that allows a human. So now the focus is on the human having visibility into this platform. Now, it's a very vanilla setup at the back. It's just a real-time key value data store that feeds information back on what's happening on Alice. And you can see those lines all across. They spread all the different domains, and that's all interactions. And one example might be, you can see those red lines. These lines are moving across, and it's all listening to events and who's doing what's happening. So a data feed might come in, and that particular data feed, the portfolio side might want to listen to that and also act on that. So you get this interaction, and the key is for us as a human to look at this thing and know what's going on. So the whole team has got sort of Alice on the side, that gives visibility in each of their domains, what they're busy with, where's the problem, so that you can frictionally develop and move forward. The second thing is pretty cool. It's not as serious, but it's this whole human. How do we deal with Alice? And it's all about standardization. Now, however you've got your processes set up, is having a very standardized entry point takes a lot of friction away from that process. So in this case, it's computers love a YAML file. So we specify all the parameters in a YAML file, and that's the entry point. There's no, from a human point of view, you don't think about Dockerization. You don't think about where do you want to run this thing, how much CPU, GPUs, distributed or not you want. You just run your code, you establish a contract between the platform. And in this case, is by standardizing almost like a think once approach, you make it simpler for the human to actually interact. And then thirdly is you've now got this balance between like Alice versus human versus combination. And in the next few slides, we're going to talk about, we'll just show you some examples of how we've tackled it. Cool. So starting off with data engineering, it's no new concept. It's hard. Doing one pipeline is super simple. Doing hundreds of them daily or real time, it becomes complex. There's nice tailwinds on things like Apache Beam and all these tools available that really makes it easier, but it's still hard. Now, Alice, the framework enjoys that because it scales. It's once you've automated those things, you take a lot of it away now. But what about inconsistencies? And this is the recent example. We get a file once a day, and this, if you can look at on the left there, you'll see there's a semicolon and a comma. Those are the two different files. Now, for a human, it's like super basic. Find, replace. If you're in Excel world, or it's like a very simple. Now, you can either have the vanilla way of the file comes in and the system fails, and you go and look at the error logs and try to figure out what exactly went wrong, or you could handle this. So how we've structured this in a, because remember, Alice is also not part of the team. If it was Zander's role to actually pass that thing, he would come to me and say, Jan, please, I've got this rule, I need to change it. Can you help me with that? So cool, I'll find and replace. So how we've done it is we've said, okay, cool, Alice enter Ubuntu state. Now, Ubuntu means, I had to look it up, but enter, it means Zulu. It means a person in Zulu. So this Alice moves into it's a bit of a play on words, but you can see there's like a tiny little blue dot there. And at the bottom is that Ubuntu 1, one of the services in Ubuntu state. Now, we don't, as a human, look at Alice the entire time. Like, I don't look at Zander and wait for him to act on me and talk to me. We've got a central place, like most of you have like either a Trello or a Asana or some project management platform where you get your. Now, this is an event. Alice needs help. And so instead of failing and going in error log, you actually go into this Ubuntu state, which interface, in our case, we use Asana just to manage all our workflows. It goes and, because it listens to it, it creates a task. So immediately I get in the morning, I get a file or a task and say, hey, Jan, please help with this. So it's not a system failing, it's as if somebody else asked me to help with this. So that's the sort of one way that it becomes quite frictionless, because it's not a system thing. You're not in a system zone. You're actually focusing on the domain side of things. The next day, the particular provider contacted all the clients and said, listen, there was a new system upgrade, et cetera, but it's a very simple example. So on its own, it looks very basic and stuff, but once you start scaling it and you get all these Ubuntu states and this interaction, you suddenly just feel like a bigger team, sort of. So that's on the data engineering. On feature engineering, again, it's nothing new for you guys. It's just the ocean of possibilities. You take something very simple. Let's take 150 columns. You've got each column maybe a dimension of time, so you've got 200 look back on that particular column, And let's say we do 6 transforms on each of those columns. Immediately, just timing those together, you get 180,000 features. So suddenly you've just got this stack of. So it becomes a problem. So what we've done there is, because a lot of these problems you can break down into smaller components. And by doing that, you can then distribute. Now, there's a lot of tailwind. The Amazons, the Googles, the Azures. There's just a lot of tailwind around distributed hundreds and millions of, and IBM, sorry, hundreds and millions of things horizontally, or horizontally. So on the left-hand side, this is just one example. So every node is a VM, and it just goes to sort of infinite numbers. And then on the right is a visual heat map of, in this case, it's those machines probably, like, let's say it ran for about 2 hours. The end result is this heat map. Now, we as a team use it to then quickly see where there are potentially signals, where there's, and that's part of the feature exploring side of things. And it's just one example of how how you could combine a human which likes visuals. This visual can then be discussed with the investment team. So looking at going on the ML side, I'm going to just ask Zander to just show some examples.
Sorry about that. Took a while. Cool. As Jan mentioned, I'm Zander Lee. I'm a machine learning engineer at Alice. So we are an investment house, which means we have a team of analysts that their main job is coming up with good investment ideas. So they have to look at a bunch of stocks and perform some sort of screening, because there's a lot of companies in the world, and you need to do a proper deep dive to truly understand how well they're going to perform. And to be able to do that, you need to limit the amount of companies you're going to look at. So what we wanted to do is use machine learning to make this process better, more effective, faster, and more efficient. So that instead of having analysts spending time to refine what stocks they're going to look at, we can use machine learning to do this refinement step for them. So this is an example of where we've applied machine learning to reduce friction in our already existing processes. So as we mentioned, in a lot of real-world data, and especially in finance as well, you've got some features that people calculate, some handcrafted features that people engineer that they call factors, and you've got some signal that you want to extract from this data. You want to understand, is a company going to perform well, or are they not going to perform well? And to get to that answer, it's not just a simple linear combination of these factors. It's a very complex, nonlinear process that you have to look at. So that's where the friction for the analysts are introduced. They need to understand and be able to look at all of these different factors and high-order combinations of them. So just an example of what they used to do is they'd have some visualization that they look at, maybe all of the different factors or some pairwise interactions, because if you've got a bunch of factors, you can't really plot more than 2, maybe 3 to look at it. So what we wanted to do is to use deep learning to remove the friction from this process, to be able to pre-filter, basically, to do pre-screening so that they can spend their time doing what's important to them, which is actually doing the research, trying to figure out what's going to work, instead of spending hours or weeks doing this sort of slow filtering process. So this is something that machine learning can give us. But the problem there is, by implementing machine learning, there's another set of problems you're introducing. So from the outside world, machine learning sometimes feels like this, where you've got some data, you shove it into your black box, you shake the box a little, and some answers pop out. And if you don't like the answers, you shake the box a little more. But this is quite a complex problem, and it becomes very difficult very quickly when you think about all the different things you have to think about when building models. So let's run through a basic example. In the real world, you don't always have a nice, clean regression or classification problem. You can formulate your problem as either one of the two. And you need to try this out, because you can get different results depending on exactly how you phrase your problem. There's also, you have to decide what label you use. If you're not trying to classify images or do some object detection, it can be quite difficult, because you need to decide what is the actual target you're trying to model. And this can introduce even more hyperparameters that you have to think about. Then there's all the usual modeling stuff, which is, do you use fully connected networks? Do you use CNNs? Do you use RNNs? In our case, it's a time series problem, so CNNs and RNNs are quite applicable. There's other things, how many layers, etc. And the amount of dimensions you have to think about very, very quickly explode. And there's a lot of models you have to run if you want to do a grid search to get this, to find the right architecture for the problem that you're trying to solve. And there's also always domain-specific things you have to think about as well. So in finance, maybe we want to test out our models in different markets. We want to try sector-specific models that model individual sectors. And there's also the time component. Do we train a single model on all the history? Do we train quarterly models? These are all domain-specific questions that you always have to try different combinations. You can't really automate that. But some of this you can automate. Some of this you don't have to search yourself or do a grid search. And you can instead try and figure out how can we instead learn a model architecture that is going to fit our problem, that is going to solve our problem well. And thankfully, there's a branch of research focused on this called neural architecture search, which is something we found extremely helpful to try and to automate the search for good architectures. Instead of using hand-designed architectures or doing a simple grid search, you can have a model that learns a useful architecture specifically fit for the problem you're trying to solve, which is key. Some of these architectures are built for vision problems or they're built for NLP, and you can't directly transfer them to what you're trying to do because the data you're working with is different. The problem you're trying to solve is different. And these neural architecture search algorithms have achieved state-of-the-art results in something like computer vision, and we found them incredibly helpful as well. So the message here is to use a machine to do something humans aren't good at. We aren't good at this sort of high-dimensional search, so instead automate that and let a system do it for you, which can do it better.
Cool, thanks, Zander. So just the last example is on, remember we said portfolios, all we do is take those machine learning predictions and you feed them into the investment team. Now, to explain a black box to an investment team is not a priority for them. So you sort of got to go to get your predictions to them. Now, these are some of our analysts. This is based in Johannesburg office. You've got Mo on the top right, Takira at the bottom left, top is Rob, which is our head portfolio manager. And they're fundamental investors. They've got in their DNA, they've got just markets. Now, they have a pretty robust, solid framework where they operate in. So when you look at their systems, they think about in terms of these 6 steps. And the particular one is, so you've got sources of information, and then you end up with this sort of level 1, 2, and 3 section. And all it is just a framework to iterate with ideas. So an analyst will come up with an idea, and we'll do the different levels of investigation. Now it's cool. So this is their process. It's got nothing to do with Alice. It's nothing to do now. So I'm almost done now. So to integrate this is, what about putting Alice into their team? So we made an analyst because their team works on, again, we use Asana, they work on Asana, and we just push Alice's ideas into their team. Now they love ideas because their objective is to find ideas. So if somebody can help them with some ideas, and in this way you see on the left you've got the list of stocks, you've got Rob and Simon with sort of thumbs up, provides a bit of feedback, and each idea then goes through a couple of levels. So because this is obviously online event-based setup, Alice can then track those ideas, and you can. What's become quite useful is you then cross-reference your ideas versus what they think about it, and you immediately have a sort of a natural session of, hang on, let's talk about this thing. What are we missing? Let's get more of the domain aspects in it. And for them, it's not interfering with their setup. It's not like some new Excel file that we need to review and please get back to us. It's part of their process. It's completely seamless. And it's almost as if they don't know Alice generated this idea. So and that is what we obsess about, the sort of frictionlessness of it, so that you can get to this point. So in closing, it's just through a fine balance between us and Alice, or the technology and the human talent. If you can bring those two together, like you get to a point where it's like, this is elegant. You often as a coder, you're like, this is cool, this piece of code. And when you get to that level of integration, it just releases sort of time and focus to find those opportunities or solve that particular domain problem. So with that, I just want to say thank you to Zander. This thing is buzzing. So it's, Alex, his team, great job with the conferences and this momentum behind it. Yeah, so thank you. We are, if there's anybody interested, we are keen to chat with anybody who's interested in this stuff. We are recruiting, and there's a couple of links. We'll put this also on the site. Cool. Thank you.
That was so awesome. I used to work in finance, and I would have dreams about stuff like this, but it's so cool that you guys are actually building it. And it's like way cooler than what I used to dream about. That was awesome. Does anyone have, so it's supposed to be like TN posters now, and we're like almost on time, so I don't think anyone will feel bad if you leave, but I think we should take some questions, because that was awesome, and I for one have questions. So if anyone has questions, please raise your hand, and let's get started. No one? Am I gonna have to like call names or something? No questions? Okay, I have a question. That was awesome. So, can you give a bit more color on the kinds of data that is being ingested into Alice, and whether you like manually write ETL for each of those data types, or like how do you think about managing, potentially thousands of time series? Some of them might be text. And as an addendum, I'm curious if you are doing anything with text.
Yeah. Yes, data is complex. It's Stuart. You know the game. It's a boring side of the thing, but if you don't get it right, it's a complete stuff up. Firstly, there's a lot of technologies and sort of tools that became open source and available as managed solutions. Things like data flow. There's a great Apache Beam, so the open source. It makes those things super simple. So there are a lot of tailwinds. Secondly, if you have a very clear pattern of how you do ETL, whether it's ETL or ELT, but you have a very clear pattern, so that if you find something, you almost have a template bank where you slot these things in. We've looked at, obviously there's a lot of tools in the industry, in sort of enterprise stuff that you can buy, but there's often like that custom little odd thing. One example was, for example, the SEC filings. It's a daily file that is generated. It's a gig zip file. You've got to unzip that gig, you've got to clean it, you've got to parse it, you've got to like take all the attachments out. And if you want to look at some particular small section called maybe the risk factors and look at the sort of interpretation of that, to get a custom tool to do that becomes complex. So like the whole what tools do you use? You've got to always think about will they interfere with the process or not. So with the data side, we've just realized that it's all about having a very consistent pattern. Another pattern that just works quite well for us is the bridge pattern. So you've got two sides of the bridge. You've got this swamp that drops a file. It doesn't care what it looks like. The bridge then picks up that file and pushes it. So it's a simple concept, but it's almost like when you actually implement that, the one portion is go to the website, download the stuff, download whatever you need, and drop it there. Once you've dropped it there, your responsibility on the swamp side basically, is done. The bridge will then pick it up. So when you build the bridge, you just think about parsing, just that file. Now, with things like these cloud functions, Lambda functions, all those things that's becoming more and more serverless, it's like perfect, because this function just listens to that bucket. And the minute you drop a file there, it just passed and into your lake. So it's all those it's like a simple thing, but it becomes super scalable if you can break your problem up into very small pieces. So instead of have a Apache Beam setup or something very simple, you just have this pattern and you just copy paste, and it just works. It's way more cheap for a lot of these things. So just having decent patterns, I guess, is cool.
I was actually Googling like the Google Cloud Platform command line tool. I was looking at Stack Overflow, and then I was like, oh shit, that's Jan. And Jan was like answering questions about how to use the GCP command line tool. So like they're really actually in the trenches and doing all this. So sure, no other questions? Like, okay, well thanks again. Let's thank Jan and Zander again.